water, earth, fire, air. Aristotle may not have had a poster of the periodic table on his bedroom wall growing up, but he sure did have an idea of what everything on Earth was made of. That idea was very, very wrong, of course, even if it did help spawn a beloved television series. But over the following millennia, scientists slowly worked things out. By the time Dmitri Mendeleev published his original version of the periodic table, in 1869 there were 63 elements that scientists knew made all of the matter that we can see, touch, and so forth. Part of that was thanks to advances in scientific theory, like Dalton's concept of the atom. Part of it was thanks to advances in scientific methods and technology. But the path from 63 to the current 118 elements was not straightforward. In fact, there were many times scientists thought they had discovered a new element, but didn't. So many, in fact, you could make a SciShow list show about it. Here's a lie that your teacher might have told you when you were young. Sunlight is made up of all the colors of the rainbow. And by lie, I mean it's so close to true, almost no one is going to call out that teacher. Except for when it actually matters, like right now. In the early 1800s, the German glassmaker Joseph von Fraunhofer split sunlight up into its constituent colors using a device he invented called a spectroscope. And he found 574 dark lines in the otherwise full rainbow. In other words, a bunch of colors were missing. These lines turned out to be super important for chemistry, physics, astronomy, and optics. Fraunhofer's discovery was, and remains, a pretty big deal. He was the first to document these spectral absorption lines, caused by atoms absorbing specific amounts of energy from light that's passing through. Because when you're dealing with light, energy corresponds to wavelength, that is, color. Then, in the 1860s, some other German scientists, including Robert Wilhelm Bunsen of Bunsen burner fame, found that absorption lines had not at all evil twins called spectral emission lines that show up when you split up the light coming from an element when it's burning. Both emission and absorption lines are the result of an atom's electrons jumping between energy levels. When it's emission, the electron is emitting that energy, so it's dropping down some number of levels. When it's absorption, it's the opposite. The exact amount of energy, and therefore the exact color of the light, depends on several factors, including how many electrons are involved and which levels they're jumping between. Both of these lines act like chemical fingerprints, because each atom has a unique set of lines that they produce. So element hunters started using spectroscopes to split light from all sorts of places to find unique new fingerprints, and therefore elements. Remember that this is right around when Mendeleev is coming up with his periodic table. He's arranged the known elements according to atomic weight, but he realized that there are repeating patterns of properties. When he mapped it all out, there are actually gaps where unknown elements might be, and that's where people started. During a total solar eclipse in 1869, two Americans named William Harkness and Charles Young split the light coming from the sun's corona, the only part that you can see during a total solar eclipse, and identified a green line in the emission spectrum that didn't correspond to any known element. In other words, they claimed they discovered a new element. They dubbed it Coronium, and assuming their discovery was legit, they'd find themselves in excellent company. Helium was discovered in the sun's spectrum just 1 year earlier. And earlier that decade, both rubidium and cesium were discovered using spectroscopy, although by looking at more down-to-earth sources. So it was reasonable that there might be another new element in the sun. But coronium always bugged scientists because it couldn't be isolated and studied for its other properties. Eventually, in 1940, that's a whopping 71 years after its initial discovery, two scientists named Grotrian and Adlin found the true culprit. It wasn't a new element that was creating this weird green spectral line. It was boring old iron, or rather, iron that had gotten so hot it was no longer boring. See, not all iron atoms will emit the exact same spectral lines, nor will atoms of any element. A spectrum also depends on how much an atom is ionized, how many electrons it has compared to the number of protons in its nucleus. On Earth, iron ions tend to come with either a +2 or +3 charge, meaning it's lost 2 or 3 of its electrons. To knock off more and more electrons, you need more and more energy, and it's harder and harder to do. Enter the sun's corona, where temperatures are in the millions of degrees and iron can be ionized 13 times over. The resulting spectral lines are so shifted they become utterly unrecognizable as iron. So that was one problem solved, but it took so long there was time for astronomers to make yet another mistake before they realized they even had one. Around the year 1864, William Huggins used his telescope and spectrograph to observe the Cat's Eye Nebula, a cloud of stellar debris surrounding a white dwarf, the remnants of a star too small to end its life with a supernova. Astronomers call these things planetary nebulas, despite having nothing to do with planets, but we don't have time to get into the history of that mistake. Like Harkness and Young before him, Huggins also observed an unusual green line that didn't correspond to any known element, not even coronium. So he concluded that some portion of the nebula must be made of yet another element. Proposed names included Nebulium and Nebulium, and their Greek counterparts Nephium and Nephilium. Nebulium seems to be the one that stuck. Or at least it did until 1927, when scientists figured out that this green line was actually created by doubly ionized oxygen atoms. The reason Huggins and others didn't realize this sooner is because the density of a planetary nebula is crazy low. There's a few hundred particles in every cubic centimeter of a nebula compared to the 10 quintillion particles per cubic centimeter in the air you're breathing right now. The only places you find on Earth with densities like this are the ultra-high vacuum areas of the Large Hadron Collider meant to mimic interstellar space. Because of this, atoms with excited electrons don't have the opportunity to lose that extra energy through collisions with other atoms like they would on Earth. Instead, all they can do is a big jump back to their lowest ground energy level, which makes for a really weird spectral line. In fact, astronomers still call spectral signatures like this forbidden lines because they break normal Earth rules. But forbidden or not, the lines weren't caused by a new element. They were a boring known element doing something decidedly unboring and unknown. So no more Nebulium. Despite setbacks like these, the periodic table really was filling out as we moved into the 20th century. The race was on to plug those last few holes where scientists knew an element needed to go. One of those holes was almost smack dab in the middle of the table, element 43. We now know it as technetium, but many people claimed to discover it through the decades and tried to name it something else, such as davium, lucium, and neponium. But you won't find any of those names on your bedroom poster. In 1925, Otto Berg, Walter Nodak, and Ida Tack, who married Walter and became Ida Nodak the following year, claimed they discovered both element 43 and 75. They named them mesurium and rhenium respectively. Because 43 and 75 appear in the same column as manganese, many element hunters thought they'd share similar properties as manganese and might also occur in the same kinds of ores. But Walter and Ida thought they might actually resemble their horizontal neighbors on the periodic table, so they investigated ores containing those elements instead. After melting samples down and subjecting them to a suite of chemical reactions, to extract and isolate any hidden elements, they passed the results to Otto. Otto then used his expertise in X-ray spectroscopy to confirm there was anything to actually discover. This kind of spectroscopy was only a few years old at the time. It required shooting electrons at an element so that it absorbed a bunch of energy, and when its atoms released that energy as X-rays, the wavelengths of those rays would be related to the element's atomic number. The team's evidence for rhenium was accepted by the International Union of Pure and Applied Chemistry, or IUPAC for short. The people who get to decide when an element officially gets discovered and what its name gets to be. But the evidence for mesurium wasn't convincing or reproducible enough for them. In fact, there has since been quite a lot of scientific argument about whether the Nodaks and Berg actually did find element 43. But in 1937, credit for the discovery ultimately went to Emilio Segre and Carlo Perrier. Their research started with a piece of scrap, irradiated molybdenum from Ernest Lawrence's lab at Berkeley. So props to that person for being willing to ship the thing over to Sicily. Lawrence eventually got an element named after him, so don't feel too bad about him missing out on this particular discovery. As element 42, molybdenum is just one proton shy of its neighbor 43. And over the course of several months of experiments, the Berkeley plate had been bombarded by oodles of deuterium atoms. Deuterium is a heavier version of hydrogen, with the standard 1 proton but also 1 neutron. Given the right conditions, it can fuse with molybdenum to create element 43. And from this plate, the Italians had isolated enough atoms to convince the chemistry authorities. The name they chose was technetium, from the Greek word for artificial, because thanks to all that deuterium bombardment, it was the first element produced by humans rather than nature. But of course, it was far from the last. In history at least, it's definitely the last before our ad break.
It's that time again where I get to tell you about Brilliant, a company that we've worked with for years. Brilliant helps you excel in math and coding with lessons in algorithmic thinking. First, you'll build a foundation in algorithms, then you can modify your algorithms and test them to make sure they work and find their limits. Finally, you'll learn how to optimize algorithms for top performance. With Brilliant's motivating challenges, you can accomplish your goals and become a stronger programmer. To learn for free on Brilliant for a full 30 days, go to brilliant.org/SciShow, scan the QR code on screen, or click on the link in the description. They're also giving you unlimited daily access to everything on Brilliant with 20% off an annual premium subscription. Thank you to Brilliant for supporting this SciShow video.
1 year after Berg, Nodak, and Tack claimed to fill the hole for element 43, two teams fought for the rights to name element 61. The team based in Florence, Italy wanted to name it Florentium. The team based in Chicago, Illinois wanted to name it Illinium. Both claimed to have discovered the element based on faint spectral lines they measured in the light that was passed through samples of the element. But nobody else could replicate their experiments or isolate a chunk of the element. It turns out there's a pretty good reason for that. Element 61 is so radioactive, even the most stable version has a half-life of 17.7 years. If you were given a 1 kilogram chunk of it on the day you were born, you'd have only 500 grams left by your 18th birthday, 250 grams by your 36th, and so on. The Earth, of course, is way older than you. A 1 million-year-old rock that started with a kilo of element 61 inside won't have a single atom left. It's basically impossible to find in nature. So what had the Italians and Americans discovered? Probably some lines coming from contaminants in their samples. By which I mean elements they already knew existed. The real element 61 would stay hidden until nuclear reactors were built. With access to that technology, scientists could create radioactive material with an even higher element number. And when that stuff inevitably decayed, enough could turn into 61 to get detected. In 1945, a group from the Oak Ridge National Laboratory in Tennessee started looking at the spent fuel from their nuclear reactor, which had been producing plutonium for the atomic bomb. They separated out the different elements using a technique called ion exchange chromatography, which sorts and filters things based on their charge, size, and chemical properties. This allowed them to find enough element 61 to be sure of their discovery. They named it Promethium, after the Titan from Greek mythology who introduced humans to fire. And while nobody wound up chained to a rock with an eagle pecking out their liver, they all probably experienced some negative side effects from their research given the constant threat of radiation poisoning and all. For our last two elements, we're going to tackle them together, because we're dealing with the same guy who thought he discovered both of them around the same time. Take a look at your nearest periodic table, bedroom poster or otherwise. You'll notice that basically all of the heavy elements past lead or so are 100% radioactive. And once you pass uranium, the half-lives are too short for you to find them in a random rock or whatever. While this tells scientists something interesting about how atoms are organized, it also poses a problem for anyone trying to find and study these elements. So like technetium and promethium, they need to be made. But let's step back a moment. One of the ways a radioactive atom tries to become more stable is known as beta decay. A neutron splits into 3 new particles, a proton, an electron, and an antineutrino. Only the proton stays in the nucleus, and the other 2 are ejected from the atom entirely, so we don't care about them right now. But since it's the number of protons that determines what element the atom is, you've now got yourself a new element. And in the 1930s, scientists figured that we could harness this power to create new elements at will. At that point in history, uranium was the last element on the periodic table. But if you took a lump of uranium and bombarded it with free neutrons, some of the uranium atoms would absorb those neutrons and become even more unstable than they already were. Then those atoms would undergo beta decay, turning neutrons into protons, and voila, you've got yourself a new element with a number above 92. This was the science behind Enrico Fermi's 1934 claim that he'd discovered elements 93 and 94. He and his collaborators looked at how quickly the uranium and thorium they'd bombarded with neutrons decayed. The curves they charted didn't look like those of uranium, thorium, or any other element down to radon. So they concluded they had found something new and heavier than uranium. Fermi named 93 Ausonium after the Greek name for Italy, and 94 Hesperium after yet another name for Italy found in some Latin poetry. We get it. The guy loved Italy. But in 1934, no one knew about a pretty important phenomenon in particle physics, nuclear fission. An atom can also get broken apart by shooting neutrons at it. In other words, Fermi may not have made elements in the 90s, he may have made much lighter elements that everyone had already known about. But because he assumed atomic numbers could only change 1 or 2 protons at a time, he only looked in the region of the periodic table right around uranium. You can probably guess what later experiments revealed. Yep, Fermi had, in fact, not created elements 93 and 94. He had made a bunch of barium. And you know who was the first person to figure all this fission mischief out? Ida Nodak, the almost discoverer of element 43. Nodak wasn't the only critic of Fermi's discovery, but that didn't stop the Nobel Prize Committee from awarding him the Nobel Prize in Physics in 1938 for, quote, his demonstrations of the existence of new radioactive elements produced by neutron irradiation. By the time Fermi gave his Nobel lecture, there was so much evidence he might be wrong, he added a footnote admitting his mistake. A couple years later, in 1940, Americans found the real 93 and 94 using a different method. Instead of using neutrons, they shot their uranium with helium nuclei to make element 94, which then decayed in a different way to create 93. 93 was named Neptunium, and 94 was named Plutonium, after the planets beyond Uranus. Fermi, meanwhile, did not have to give back his Nobel. And he was good enough at nuclear and particle physics that the scientists who discovered element 100 chose to name it fermium. There's also Fermilab, the Fermi paradox, an entire class of subatomic particles called fermions. In terms of legacy, he's doing all right. So if you're out there waiting impatiently for the next major update to the periodic table, element 119 or otherwise, I recommend passing the time by telling your friends, distant relatives, and internet strangers about the guy who won a Nobel Prize for discovering two elements that don't exist, or any of the stories we've covered today.